Good morning to all of you. Today I am here for heterocyclic compound. Introduction. Heterocyclic compound are defined as a cyclic compound which has heteroatoms at one or more corner of a ring. The heteroatom may be oxygen, sulfur, nitrogen. A heterocyclic compound may or may not be aromatic in nature. Substances such as alkene oxide, cycloanhydride, etc. are heterocyclic in the strict sense but are not generally considered as heterocyclic sense. They are highly unstable. Heterocyclic are generally 5 or 6 member ring. They are stable and possess certain degree of aromatic properties. Heterocyclic compounds are abundant in plant and animal products. Alkaloids, dyes, drugs, protein, enzyme, etc. are the important representative of this group. Classification. Heterocyclic are generally classified on the basis of the size of heterocyclic ring present. A. First member ring, heterocyclic. Some important member of cycles are furan, thiophenes, pyrrole. We see a heteroatom at one corner of a 5-member ring. B. 6-member heterocyclic. These are 6-corner ring have heteroatom at one or more corner. Some important member of these class are pyridine, peran, thiopheran. C. 5 or 6 member heterocyclic containing 2 heteroatoms. Some 5 or 6 member ring contain 2 heteroatoms are given below. First, 5-member ring compound with 2 heteroatoms. Imidazole, oxazolene, pyrazole. 6-member compound with 2 heteroatoms. Pyrimidine, pyrazine, pyridazine. 6. Condense 5 or 6 member heterocyclic. These compounds constitute 2 or more rings which are fused together. The fused ring may be partially carboxylic, carb-cyclic and partially heterocyclic. Some important members of this class nomenclature. Heterocyclic compounds are generally by their common name. The systematic IUPAC name of heterocyclic compound are obtained by combining following prefix. Order of seniority. Prefix suffix. 1. Oxo for oxygen, OLE, 6-member ring. Second, thio for sulfur, suffix 6-member, for 6-member INE. Nitro, suffix for nitro, prefix for nitro, azo, suffix for 7-member ring, EPINE. Prefix for sulfur, phosphorus, phosphor. Prefix for boron, bora.
The terminal A of the prefix is usually dropped when combining with the prefix and suffix. According to IUPAC system, pyrrole is named as azole, furan as oxazole, thiophene as thiol, and pyridine as azine. In case then one heteroatom is present, the prefixes are placed in order of seniority, first oxo, then thio, etc. The simple heterocyclic compound containing one heteroatom are numbered in such a way that the heteroatom get the lower number and the numbering is continue in the anti-clockwise direction.
In case Greek letters are used, the position next to heteroatom is designed as alpha, followed by beta, gamma, and so on. If 2 or more different heteroatoms are present in a ring, the numbering is done in such a way that the oxo get preference over sulfur and sulfur is in turn get preference over nitrogen. Aromaticity of 5-member ring heterocyclic compound. All the 5-member heterocyclic compounds such as furan, thiophene, pyrrole are aromatic compounds since the number of pi electron in there are accordance with Huckel rule. According to this rule, the aromatic compound should be first cyclic, second planar, third should have delocalized 4n plus 2 pi electrons. It should be fairly stable. Each of these 5-member heterocyclic have 6 pi electron and it is in accordance to Huckel rule, n is equal to 1. Furan, thiophene, pyrrole are the simplest 5-member heterocyclic compound. From the structure of these compounds, it is expected that they possess the property of conjugated diene and an ethers, a sulfide or an amines. These compounds are found to be show electrophilic substitution reactions such as nitration, sulfonation, halogenation, Friedel-Crafts alkylation, etc. Also, they show Riemer-Dimer reaction, coupling reaction, and diazonium salt, and also some addition reaction. These compounds clearly show aromatic character. The aromatic character is also provided by their heated of a condensation. The value of heats of a condensation should show resonance stabilization to the extent of 20 to 28 kilocalorie per mole. The resonance energy of this compound lands significantly degree of stabilization with result to aromatic character. The aromaticity of these heterocyclic compounds depend on the 2 electrons which the heteroatom contribute to the pi electron. In the case of pyrrole, these requirements depress the nitrogen atom of the pair of electrons commonly associated with organic amine. Thus, pyrrole can form a salt only at the extent of aromatic character. Hence, pyrrole is a weak base which in fact is protonated preferably at a ring carbon in a strong acid. Pyrrole in presence of acidic presence give measure 1 at one position, second position. Furan is comparatively less basic due to the high electronegativity of oxygen and render it more stable to acidic. Structure of 5-member heterocyclics. The simple 5-member heterocyclics are furan, thiophene, pyrrole. For molecular formula, the analytical data reveals that the molecular formula of this compound are furan C4H4O, thiophene C4H4S, and pyrrole C4H5N. Second, addition of hydrogen. On catalytic hydrogenation, each of these compounds are found to add 2 molecules of hydrogen. This shows the presence of double bond in each of them. Furan plus 2H2 in the presence of nickel give tetrahydrofuran. Thiophene plus 2H2 in the presence of nickel give tetrahydrothiophene. Pyrrole in presence of 2H2 in the presence third, electrophilic substitution reaction like benzene. These compounds are found to show electrophilic substitution reaction like chlorination, nitration, sulfonation, etc. They also show Riemann-Tiemann reaction, coupling reaction. They show that these compounds are aromatic in nature. For the above properties, the above 3 5-member heterocyclic are best represented as conformation by synthesis. The structure of these compounds are confirmed by the following synthesis. For this, the starting material is 1,4-dicarbonyl compound then changed to enol forms. After enol form, when we react enol form with the P2O5 and heat give furan. When we react enol with P2S3, it gives thiophene. When we react enol form with NH ammonium carbonate, it gives pyrrole. Limitation of diene structure. The above diene structure failed to explain the following properties. First, these behave like benzene and undergoes electrophilic substitution reaction. Second, unlike secondary amine, pyrrole lack basic characteristic. Third, they undergoes addition reaction but their tendency is restrained for a diene. Fourth, furan, thiophene and pyrrole are flat molecules. Orbital structures. The orbital picture of these compounds give an answer to the above mentioned limitation in their structural formula. Electronic configurations of carbon in its excited state is and of nitrogen in its excited state. Configuration of carbon 1s2, 2s2, and also we know the excited or configuration of nitrogen there is given below. First, pyrrole. All the carbon atom and nitrogen atom in their compound is sp2 hybridized. Carbon has 3 sp2 hybridized orbital and an unhybridized orbital each containing 1 electron. Also, a nitrogen atom has 3 sp2 hybridized orbital and a p orbital unhybridized. All these containing an odd electron each. The heteroatom contain 1 sp2 hybridized orbital which contain a pair of electrons. sp2 orbital of adjacent atom overlap to form sigma bond, and also sp2 orbital of each carbon or nitrogen atom overlap with orbital of hydrogen atom to form a sigma bond. The unhybridized p orbital then overlap sidewise to form a cyclic delocalization pi molecular orbital containing 6 electrons, embracing all the 5 atoms of rings. The delocalization orbital would be made up of a 2 pi electron cloud, one above and one below the plane of ring. Second, furan or thiophene. Furan and thiophene are also flat molecule. Electron configuration of carbon is given. Oxygen and sulfur in their excited state are respectively. They also involved hybridization a carbon. In these two compounds also they are cyclic sigma electronic cloud containing a 6 electrons above or set of electrons above or below the plane of ring. Out of 3 sp2 orbital of oxygen or sulfur, 2 have an odd electron each, while the third has a pair of electrons. The heteroatom form 2 sigma bonds with the adjacent carbon atom. The electron pair in the third sp2 orbital of oxygen or sulfur remain unshared. The unhybridized p orbital containing 2 electrons form a part of delocalized electron cloud by overlapping sidewise with the p orbital of carbon. The orbital structure of furan and thiophene can be shown. The delocalized 6pi electron cloud make furan and thiophene aromatic in nature. Clearly, these compounds show electrophilic substitution reaction. Explain for the unique behavior of pyrrole. First, as both the p electron or n nitrogen are involved in the formation of delocalized pi electron cloud, it is not left with any electron, thus it lacks basic character. Second, the presence of electron cloud of 6 delocalized electron make the compound aromatic. Huckel rule. Third, it undergoes addition reaction with difficulties. The reaction is that the two double bonds in pyrrole are not true double bond due to resonance. Fourth, due to involvement of sp2 hybridized pyrrole is a flat molecule. From the value of heat of combustion of these three heterocyclic, these resonance energy is found to be 22 to 28 kilocalorie per mole. These values are much greater than the conjugate dienes. Resonance in 5-member heterocyclic, furan, thiophene, and pyrrole are considered as resonance hybrid of a number of contributing structures. This approach describes pictorial result of the delocalization of heteroatomic lone pair of electrons. Out of these structure, first is the major contribution to resonance hybrid as it does not involve charge separation. Structure second and third are slightly more significant than those of fourth and fifth due to smaller charge separation. For benzene, two uncharged resonance structure can be written, whereas only one resonance structure for furan, thiophene, pyrrole can be written in which no charge separation is involved. This is the reason that the resonance energy of these compounds are just half of benzene. Also, due to the decreasing electronegativity of oxygen to nitrogen to sulfur, resonance structure are less important in the case of furan compared to thiophene and pyrrole. Clearly, furan is the least aromatic of these heterocyclics. The evidence for the delocalization structure is also available for the bond length measurement. The spectroscopy study revealed that the bond of heterocyclic and intermediate in the length between the usual single and double bond. Recent microwave study has shown that the pyrrole molecule is completely planar and have the given molecular dimensions. These results confirm the experimental result of electron diffraction study. As the distance between carbon atom 2 and 3 and 4 and 5 are greater than that between the carbon atom of ethylene, and the distance between carbon atom 3 and 4 is less than that of between the carbon atom of ethane, and approach the carbon-carbon distance in benzene, and as carbon-nitrogen distance are less than those in trimethylamine, the molecule cannot be aquatically represented by the classical structure 1. Thus, pyrrole must be treated as resonance hybrid of which of the more important contributing structure is number 1, the major contributor. For the resonating structure, it is evident that the electrophilic substitution occur at the negative center shown above. Pyrrole, furan, and thiophenes are aromatic compound. An aromatic compound is one which is cyclic and contains 4n plus 2 pi electrons. It's such that obey Huckel rules. Here n is equal to 0, 1, 2, 3 and so on. In pyrrole, furan and thiophene, they are 2 carbon-carbon double bonds such that 4 pi electron. The lone pair of electron on nitrogen, oxygen, sulfur also join the 4 pi electron to make 6 pi electron cloud. Hence, Huckel rule is satisfied. Synthesis and reaction of 5-member heterocycles. First, furan C4H4O. Method of preparation. First, from mucic acid. It is obtained by the dry distillation of mucic acid. When dry distillation of mucic acid is it converted into furic acid, then heated, it give furan plus CO2. Second, furfur. It forms furic acid on oxidation, which in return decarboxylate to form furan. Third, dicarbonyl compound. By the dehydration of succinate dihaldehyde by heating with P2O5 or anhydrous ZnCl, give furan. Furan can be obtained by distillation of pine wood. Pahl-Carnot synthesis. A general synthesis of furan, thiophene, pyrrole derivative can be achieved from 1,4-dicarbonyl compound as shown below. Electrophilic substitution reaction of furan, thiophene, pyrrole. Furan, thiophene, and pyrrole are highly reactive toward usually electrophilic reagents. These are more reactive than benzene. The greater susceptibility to electrophilic attack is due to unsymmetrical charge distribution in these heterocyclic. As a result of this, the ring carbon atom acquires greater negative charge than benzene. Out of these three compounds, furan is more reactive than and thiophene is least reactive. Thiophene is much more stable than furan or pyrrole toward acid. This fact also greater latitude when selective condition for electrophilic substitution of a thiophene. Electrophilic substitution of these compounds occur preferentially at C2 position because the transition state for attack at this site is lower energy than that of a carbon 3 position. Since the rate of substitution at either position is depend upon the energy difference between the ground state of reactant and the particular transition state, the process which passes through a more stable transition state will occur more rapidly. The sulfonation of thiophene proceeds rapidly in 95% of sulfuric acid at room temperature to give thiophene to sulfuric acid. Such acidic conditions cannot be employed for furan and pyrrole. Also, it may be noted that benzene and its homologs are not sulfonated by the reagent. Sulfuric acid is quite reactive to cause sulfonation of anisole and thiophene. Properties of furan. A. Physical. It is a colorless liquid which boils at 33 degrees Celsius. It is insoluble in water but dissoluble in alcohol and ethers. Chemical. First, electrophilic substitution reaction. It behaves as an aromatic compound like benzene and hence show electrophilic substitution reaction. We know that in furan position 2 and 5 are exactly alike. Similarly, position 3 and 4 are alike. When an electrophilic attack, a carbonium ion result from the following resonating structure. It is clear that the carbonium ion is more stable when the electrophilic attack position 2 or 5 than when it attack position 3 or 4. Greater the number of resonating structure, greater is the stability of resonance hybrid. Clearly, electrophilic substitution take place at position 2 as it results in more stable carbonium ion. The greater reactivity of furan is due to donation of oxygen lone pair. A. Nitration. Direct nitration with a mixture of concentrated nitric acid and sulfuric acid result in the formation of resinified product. But when treated with acetyl nitrate, we get 2-nitrofuran. B. Sulfonation. It cannot be directly sulfonated with sulfuric acid, but with pyridine sulfuric trioxide at 70 degrees Celsius, we get furan 2-sulfuric acid. Halogenation. Direct halogenation is not possible at room temperature. 2-bromofuran can be obtained by brominating furic acid and then decarboxylating the product on heating. Friedel-Crafts reaction. Alkylation of furan resulting in polymerization. Alkylation in the presence of SnCl4 yield 2-acetyl furan. Mercutation. On heating with mercury chloride and aqueous sodium acetate, 2-chloromercuric furan result. This compound can be easily converted into 2-halofuran. F. Gattermann reaction. On treating with a mixture of SnCl and hydrogen chloride in presence of ammonium chloride and imine result. This is hydrolysis yield furfural. Coupling reaction. On treating with an alkyl solution of diazonium salt, azodie results. Reaction with N-butyl lithium. The lithium compound on treating with CO2 and acid yield furan acid. Diel-Alder reaction. Furan react with maleic anhydride to form an adduct. Note: thiophene and pyrrole do not show the reaction. Furan is less aromatic than thiophene and pyrrole. Reduction. Using Renal nickel, it can be reduced to tetrahydrofuran. On treating with HCl, tetrahydrofuran is tetramethyl chlorohydrin. Note: furan on heating with aqueous solution of acetic acid undergoes ring cleavage to form acetonyl acetone. Notes on the property of furan. First, direct halogenation of furan is very variously and useful. Products are seldom isolated because the liberation hydrogen chloride causes polymerization. Second, furan can also be brominated by dioxane dibromide at 0 degrees Celsius to form 2-bromofuran in good yield. Third, alkylation of furan by Friedel-Crafts reaction has proved unsuccessfully because the catalyst used in the reaction catalyze polymerization. On the other hand, furan carrying electron withdrawing group are more stable to electrophilic attack. Thiophene C4H4S. Method of preparation. First, from coal tar. The light oil fraction from coal tar distillation also contain a liquid thiophene. Little thiophene. It cannot be separated from benzene at its boiling point is quite closer to benzene. To separate thiophene, the mixture is shaken with concentrated acid to get thiophene sulfuric acid. The latter, on treated with superheated steam, yield thiophene. Second, from sodium succinate. Sodium succinate on heating with phosphorus trisulfide yield thiophene. From acetylene. A mixture of acetylene and hydrogen sulfide H2S on passing through a tube containing Al2O3 at 300 degrees Celsius yield thiophene. From phoric acid. By the reduction of fluoric acid with barium sulfide give thiophene. Property of thiophene. Physical. It is colorless liquid boil at 75 degrees Celsius. It is insoluble in water but dissolved in organic solvent. B. Chemical. It is more aromatic than furan. It is also more stable. First, electrophilic substitution reaction. Electrophilic substitution reaction take place at 2 or 5 position as the carbonium ion form in this case is more stable. If 2 and 5 position are already blocked, then the substitution is expected at the position 3 or 4. Thiophene ring is least activated for electrophilic attack due to maximum resonance structure. Thiophenes react under similar conditions as those of benzene. Thiophene does not show coupling reaction. Some common substitution reactions are given below. Nitration of benzene, thiophene give nitration reaction. Thiophene give sulfonation reaction at position 2. When thiophene react with chlorination, give 2-chlorothiophene plus 2,5-dichlorothiophene. When react with Br2, give 2,5-dibromethiophene. When react with I2 in presence of HGO, give 2-iodothiophene. Thiophene react with HgCl2 in the presence of sodium acetate, give 2-chloro-mercaptithiophene. Mercuric thiophene. Thiophene also give Friedel-Crafts reaction, chlorination, chloromethylation, and butyl. It's also thiophene also react with butyl lithium to give 2 lithium thiophene, and in the presence of acid give thiophene 2-carboxylic acid. Reduction with renal nickel and butyl result. Different product result with hydrogen palladium and sodium ammonium. Thiophene react in the thiophene give in the presence of nickel, and nickel in the presence of hydrogen give butane plus NiS. Thiophene in presence of palladium and hydrogen give tetrahydrothiophene. In the presence of sodium and ammonia give 2,5-dihydrothiophene or 2,3-dihydrothiophene. Oxidation of tetrahydrothiophene. On oxidation it forms as sulfone. Note for the properties of thiophenes. Due to high stability of thiophene in acidic condition, its Friedel-Crafts alkylation can be achieved with a wide variety of catalysts in excellent yield. Also, for the Friedel-Crafts alkylation of thiophene, both C2 and C3 position are attached in ratio varying 1:1 to 3:1 depending upon the reagent and the catalyst employed. The reason for the poor selection is due to the highly reactive nature of electrophilic alkyl cation, which attack the heterocyclic in indiscriminate fashion. Pyrrole. C4H5N. Method of preparation from acetylene. When a mixture of acetylene and ammonia is passed through a red hot tube, pyrrole is formed. Second, ammonium mucate. When ammonium mucate is heated with glycerol, mucic acid result, which undergoes dehydration, decarbonation, ring closure by elimination of water, CO2 and ammonia. For succinic dialdehyde, by warming succinic aldehyde with ammonia, give pyrrole. Succinimide. When succinimide is heated with zinc dust, pyrrole is formed. From furan. When a mixture of furan, ammonia and steam is passed over Al2O3 at 500 degrees Celsius, pyrrole results. Property of pyrrole. Physical. It is colorless liquid which boil at 131 degrees Celsius. It readily turns brown when exposed to air. It smells like chloroform. It is highly soluble in water but dissolved in ethanol and ether. B. Chemical property. First, amphoteric character, basic character. It is a weak base and react with dilute HCl to give crystalline hydrogen chloride. In the presence of oxygen, the crystalline hydrogen chloride polymerizes to brown rings. Second, acidic nature. Pyrrole also behaves as weak acid and react with KOH and also with Grignard reagent to form corresponding salt. Second, electrophilic substitution reaction. Pyrrole undergoes electrophilic substitution at C2 position. It is clearly from the 3 resonating structure of intermediate obtained from the attack at C2. On the other hand, only 2 such forms are possible from substitution at C3. Clearly, the intermediate with the 3 resonating structure is more stable and hence product with substituent at C2 predominant. The substituting at C3 occur only when 2 and 5 positions are occupied. Electrophilic substitution reaction of pyrrole do not take place in the presence of strong acids. Pyrrole nitration in the presence of HNO2 and acetate. Ethyl acetate. Sulfonation SO3 in the presence of pyridine. Chlorine 0 degrees Celsius in the presence of SO2Cl2 ether. Iodination I2 plus Ki. Friedel-Crafts reaction alkylation. It gives Friedel-Crafts acylation in the presence of C2H5Cl in the presence of SnCl4. Riemer-Tiemer reaction CHCl3 plus KOH. Cold-Smith carbonation. K2CO3 aqueous and heat give pyrrole to carboxylic acid. Coupling reaction give 2-benzyl azo pyrrole. Malic anhydride give reduction. It reacts with zinc and acetic acid to give 3,5-dihydropyrrole. Catalytic reduction. Catalytic reduction yield propylidene. Oxidation. Pyrrole is oxidized by CrO3 in acetic acid to form malic imide. Ring opening reaction. With hot alcoholic hydroxyl amine, it forms dioxane of succinylaldehyde. Ring expansion. Lithium salt of pyrrole on heating with chloroform 3-chloropyridine. A bicyclic transition state is formed with break to give the product. Pyrrole is acidic like phenol. Pyrrole as well as phenol lose a proton and the respective anion form in each case is stabilized by resonance. Relative reactivity of pyrrole, furan and thiophene. Pyrrole, furan and thiophene show aromatic character like benzene. It is found that their resonance energy are much smaller. Thus, they are less aromatic or more reactive than benzene. The order of reactivity is in order. Pyrrole is much more reactive than furan. Furan is much more reactive than thiophene, and thiophene is much more reactive than benzene. Increasing order of atomic aromatic character in pyrrole, furan, and thiophene is given as pyrrole, furan, thiophene. Thiophene is most stable or least reactive out of these, as it is used into its d electron to form a large number of resonating structures and thus get stabilized to a greater extent. Furan is less reactive than pyrrole because oxygen accommodates a positive charge less readily than nitrogen. Six-member heterocyclic. The six-member heterocycles may belong to three main classes. These are: first, six-member heterocyclic contain one heteroatom. Example, pyridine. Second, six-member heterocyclic contain two or more heteroatom. Pyrimidine. Third, considering ring system containing six-member heterocyclic like quinolone, isoquinoline, purine, etc. Structure of pyridine. C5H5N. Molecular formula. From the analytical structure, the molecular formula of pyridine is found to be C5H5N. Second, aromatic character. Pyridine show electrophilic substitution reaction like benzene. It is aromatic in character. The factor which favor in its aromatic behavior are: it can be chlorinated, nitration, sulfonation. It hydroxide derivative behave like phenol. It is stable toward oxidizing agents like potassium permanganate, chromic acid, etc. Its ammonium derivative can be deazotized like aniline. Its alkyl derivative can be oxidized to acid. Its resistance addition reaction. Third, basic nature. When treated with alkyl halide, it forms a quaternary salt. It shows that pyridine is a tertiary amine, such that pyridine contains a tertiary nitrogen atom. Fourth, catalytic reduction. When reduced with hydrogen in the presence of nickel, it forms piperidine. The addition of 3 molecules of hydrogen shown that pyridine consists 3 double bonds. Moreover, pyridine is a ring of a 5 carbon atom and a nitrogen atom. Korn formula. From the above property of pyridine, Korn suggested that the following structure as shown. Evidence in support of a Korner formula. The above structure suggested that the formation of 3 isomeric monosubstituted products. The following 3 substitution products are actually formed. This support Korner formula. Second, the above structure of pyridine is also confirmed by synthesis. Pentamethylene 1,5-diamine hydrochloric on heating form piperidine, which with concentrated sulfuric acid at 300 degrees Celsius form pyridine. Resonating structure. Pyridine can be represented by the following resonating structures. Evidence in favor of a resonating hybrid structure. The resonance structure is supported by the following. First, intermediate bond length. The carbon-carbon bond length in pyridine are intermediated between carbon-carbon single bond and carbon-carbon double bond. Similarly, carbon-nitrogen bond length 1.37 angstrom is intermediately between carbon and nitrogen single bond and carbon and nitrogen double bond length. B. Resonance energy. Its resonance energy is found to be 96.23 kJ per mole, which is more than expected from a triene. Orbital structure of pyridine. The nitrogen atom in pyridine is sp2 hybridized, thus it has 3 sp2 hybridized orbital and 1 unhybridized p orbital. Out of 3 hydrogen orbital, 2 has and 1 electron each, while the 3 sp2 has a pair of electrons. The unhybridized orbital has also 1 electron in it. Also, each carbon atom has 3 sp2 hybridized orbital and 1 unhybridized p orbital containing 1 electron. Each of a 2 sp2 orbital of nitrogen overlap with sp2 orbital of carbon atom, forming 2 CN bond. Also, remaining 2 sp2 hybridized orbital of each of a 5 carbon atom overlap with sp2 orbital of adjacent carbon atom to form sigma bond. Also, 3 sp2 orbital of each carbon overlap with s orbital of hydrogen atom to form sigma bond. The unhybridized p orbital of a 5 carbon and 1 nitrogen present in a ring with 1 electron in each undergoes sidewise overlapping to form pi bond. Thus give a cyclic delocalization molecular orbital containing a 6 set of a pi electron. The delocalization orbital compare pi electron cloud lying above or below the plane of ring. Due to the dispersal of pi electron cloud, pyridine is stable and aromatic in character. Basic character of pyridine is due to unshared pair of electrons present in remaining sp2 hybridized orbital of nitrogen. Synthesis of pyridine and its derivative. First, from coal tar. During fractional distillation of coal tar, a light oil fraction is obtained from which pyridine can be discovered from a commercial use. The fraction is treated with dilute sulfuric acid. The aqueous layer is separated and neutralized with Na2CO3, and pyridine is obtained as a dark brown oil, which is further purified by fractional distillation. Second, by heating pentamethylene diamine hydrochlorine. The product formed on heating is oxidized with palladium and carbon. Third, from acetylene. Heating acetylene and HCN in ratio 2:1 in a red hot tube yield pyridine in a low yield. Hagen synthesis of pyridine and its derivative. This method involves the condensation of aldehyde, a beta ketoesters, or a beta ketone and ammonia. It involves the following steps. From pyrrole. Pyrrole undergoes ring expansion when heated with methylene chlorine or methylene iodine in the presence of sodium ethoxide to give pyridine. From picoline. Picoline obtained from acrolein undergoes oxidation with acidified KCrO7 to give nicotinic acid, which can decarboxylate with soda lime to get pyridine. Properties. Physical property. It is colorless liquid, has an unpleasant smell. It boils at 125 degrees Celsius. It dissolves in water completely and is a good solvent. It is hygroscopic. Its dipole moment is 2.26 dB. B. Chemical properties. Basic in nature. It is a base and is comparable in a strength to aniline. It is weaker than tertiary aliphatic amine. Let us compare the basic strength of some pair of compounds. First, pyridine and pyrrole. The basic character of pyridine is due to lone pair of electron on nitrogen able for sharing with acid. In case of pyrrole, the electron pair on nitrogen is involved in aromatic sets and is not able for sharing with acid. Hence, pyrrole is a weak base in compared to pyridine. Second, pyridine and aliphatic tertiary amine. Aliphatic tertiary amine are stronger base than pyridine. In aliphatic tertiary amine, the electron pair on nitrogen atom is in sp3 hybridized orbital, but it in an sp2 hybridized orbital in case of a pyridine. We know that electrons in sp3 or sp2 orbital are held more tightly by the nucleus than those of sp3 orbital. As a result of this, the electron pair on nitrogen in aliphatic amine are more available for sharing with acid than in case of pyridine. Hence, aliphatic tertiary amine are stronger base than pyridine. Third, pyridine and aryl amine. The basic strength of pyridine and aryl amine are comparable. It is due to the electron withdrawing effect of benzene. Hence, electron pair on a ring at a nitrogen atom is less available for sharing with acid. Fourth, basic strength of piperidine and pyridine. Piperidine is a stronger base as compared to pyridine and gives the reaction of a 2-degree aliphatic amine. It is not an aromatic compound and lone pair on nitrogen atom in it is fully available to protonate. It reacts with HCl to give piperidine hydrogen chloride. Moreover, the lone pair on nitrogen atom is present in sp3 orbital, hybridized orbital. It is not tightly held as in case of pyridine, in which it is present sp2 hybridized orbital. Due to strong basic character of pyridine, it shows the following reaction. First, action with acid. It forms salt with acid. It is a monoacidic base. Second, treated with CH3I followed by a most Ag2O, an alkyl pyridinium hydroxide result. Note, pyridine is more basic than pyrrole. In pyridine, 2 sp2 hybridized orbital of nitrogen atom overlap with sp2 orbital of 2 carbon on either side. The unhybridized orbital form a part of delocalization electron cloud. Thus, the third sp2 orbital containing the lone pair of electron is available to the acid. In case of pyrrole, all the electrons are shared and no electron pair is free to react with acid. Thus, pyridine is more reactive than pyrrole. Second, electrophilic substitution reaction. It resembles benzene in aromatic character and so electrophilic substitution reaction. The electrophilic attack at position 3 yield a carbonium ion which is more stable than that obtained with electrophilic attack position 2. Note: when an electrophilic attack position 2 or 4 on one of the contributing structure has a positive charge on electronegative nitrogen atom, which make contributing structure unstable and contribute very little to hybrid. No such structure is formed when electrophilic attack at carbon 3. Thus, the electrophilic substitution occur at C3 since the resonating hybrid in case is relatively more stable. Note: low reactivity of pyridine toward electrophilic substitution. In pyridine, pi electron cloud is displaced slightly toward more electronegative nitrogen atom. Due to this, carbon atom of pyridine ring are left with smaller electron density than that of carbon of benzene ring. As a result, pyridine get deactivated toward electrophilic reaction. Pyridine is further deactivated because its basic nitrogen atom is readily attacked by protons present in the reaction mixture to form pyridinium ion. Thus, the nitrogen atom withdraw electrons from the ring strongly and make electrophilic attack difficult. Third, nucleophilic substitution reaction. We know that if a highly electronegative atom or a group is present on a benzene ring, then it can show nucleophilic substitution reaction. Pyridine resembles benzene with a highly electronegative group atom or group. The electron withdrawing nature of nitrogen that make pyridine unreactive toward electrophilic substitution reaction make it highly reactive toward nucleophilic substitution reaction. It is found that the nucleophilic substitution at position 2 or 4 result in the formation of a carbon anion which is resonance stabilized. The negative charge on nitrogen atom make the hybrid extra stable on nitrogen atom can better accommodate the negative charge. Attack at position 3 does not give a structure which has negative charge on nitrogen atom, thus nucleophilic substitution at position 2 and 4 more rapidly. First, with KOH. On heating with KOH at 300 degrees Celsius, 2-hydroxypyridine is formed, which is the enolic form of 2-pyridine. Second, with the phenyl lithium or N-butyl lithium, the substitution occurs at C2 position. Third, action with soda amide. Pyridine form 2-ammonopyridine and soda amide. The reaction is called Chinhe-Bettine reaction. Reduction with sodium and alcohol, it forms piperidine. B. When heated with hydrogen in the presence of nickel, piperidine is formed. C. With HI acid at 300 degrees Celsius and pentane is formed. Fourth, oxidation. Due to more stability, it is a resistance to oxidation. With peracetate acid, pyridine and oxalate is formed. Uses. It is used in reactions such as acylation, benzylation, etc. It is used as a solvent and also for denaturing ethyl alcohol. Introduction to condensed 5 and 6 member heterocycle. A number of heterocyclic compounds are known in which a benzene ring is condensed with a 5 or 6 member heterocyclic ring. Some examples include indole, quinoline, isoquinoline, etc. Pyrimidine. It is the important 6-member heterocyclic containing 2 nitrogen. The ring system is present in many natural products. Synthesis. The starting material of synthesis of pyrimidine is malonic ester. It involves the following step. Diethyl malonate react with urea and ethanol give this. When a tautomerism with this give pyridine. It is a colorless compound. It is aromatic in nature. It is a weakly basic and cannot be monoprotonated. B. Chemically. First, basic character. It is weak base than pyridine. Under normal condition, only one nitrogen of pyridine can be protonated, but under very strong acidic condition, both nitrogen can be protonated to form diprotonated pyrimidine. First, electrophilic substitution. The presence of 2 nitrogen atoms deactivates the ring for electrophilic substitution. Still, monoprotonated pyrimidine give 5-bromopyrimidine. If resonate structure by pyrimidine are written, then it is found that its C5 position remain relatively rich in nitrogen in presence of electron donating group like OH, NH2, etc. Electrophile substitution is faculty 8. Second, nucleophilic substitution reaction. First, if chlorine atom is present at C2, C5, C6 position, then it can be easily replaced by nucleophiles such as OH negative, NH2 negative, etc. with hydrazine. At 130 degrees Celsius, it reacts with aqueous solution of hydrazine to form an addition product, which then rearrange to give pyrazole. Alkylation. When treated with alkyl iodine, alkylation occurs only at 1 nitrogen, but with triethyl oxime fluoroborate, both nitrogen can be alkylated. Indole. Occurrence. Indole occur in coal tar, jasmine flower and orange blossoms. It is a parent compound of indiogotine, which is a wet dye. Preparation. Fischer-Indole synthesis. When phenyl hydrazone of pyric acid is heated with ZnCl2, it gives indole 2-carboxylic acid, which decarboxylate to indole. The preparation of indole derivative is carried out by heating the phenyl hydrazine on substituted phenol hydrazine in an approximate aldehyde ketone or ketonic acid with ZnCl2, polyphosphoric acid, etc. The mechanism of reaction is given below. Second, Medulin synthesis. This involves cyclation of an orthoacyloamide toluene by a stronger base like NaNH2 or tetrabutoxide. For example, the mechanism, it involves the formation of intermediate carboanion by the base followed by the cyclation as shown below. Quinoline. It is a colorless liquid which turns yellow on standing. It possesses characteristic odors resemble that of pyridine. It is miscible with most of organic compounds. Structure elucidation. First, molecular formula. From the empirical data, the molecular mass determined the molecular formula of quinoline is found to be C9H7N. Second, electrophilic substitution reaction. It undergoes electrophilic substitution reactions such as nitration, sulfonation, etc. like benzene. The properties show the presence of one or more ring in the molecule. Second, action of alkyl halide. When treated with alkyl halide, it forms a quaternary salt. This shows the presence of tertiary nitrogen atom in it. Fourth, oxidation. When oxidized with alkaline potassium permanganate, it forms quinolinic acid and oxalic acid. It is known that naphthalene on oxidation gives phthalic acid. It is clearly that quinoline, one pyridine ring is fused with benzene ring, which is broken during oxidation. Clearly, the structure formula of quinoline can be written as shown. Conformation by synthesis. The structure of quinoline is formed by synthesis. A. Kirchhoff synthesis. Quinoline is obtained from the reaction of aniline with glycerol, concentrated H2SO4, nitrobenzene and furic sulfate. Second, Friedel-Lander synthesis. Quinoline is obtained by condensation of orthoaminobenzylaldehyde with acetaldehyde in sodium hydroxide solution. All ring atoms in quinoline are sp2 hybridized like pyridine. The electron pair of nitrogen atom resists in an sp2 orbital and is not involved in the formation of delocalized bimolecular orbital. Due to this electron pair, quinoline can readily form an N-oxide and undergoes quaternarization. It constitutes delocalization 10 pi electron system and satisfies the Huckel rule. Quinoline can be written in the following resonating structures as given below. It is the best considered as a resonance hybrid which corresponding to that of the naphthalene is regarded to the uncharged contributing structure. The various pi electron density in case of quinoline are as shown below. Isoquinoline. It is a colorless solid with a smell like that of a benzaldehyde. It is volatile in stream, sparingly soluble in water and insoluble in organic solvent. It turns yellow on Normal stage. Storage. Structure 1. Molecular formula. From the empirical data, the molecular mass determination, the molecular formula of isoquinoline is C9H7N. Electrophilic substitution reaction. It undergoes electrophilic substitution reaction like nitration in the same way as benzene. These show the presence of one or more aromatic ring in the molecule. Third, action with alkyl halide. It reacts with alkyl halide to form a quaternary salt. These show the presence of tertiary nitrogen atom in it. Oxidation. When oxidized with potassium permanganate, it gives a mixture of phthalic acid and cinchromic acid. From this, it is clearly that isoquinoline molecule consists of one benzene ring fused with a pyridine ring in beta-gamma position. Clearly, first, phthalic acid is produced when pyridine ring is repurchased, and second, synchronic acid is obtained when benzene ring is recaptured. In synchroic acid, the position of two carboxylic acid group should the position where benzene is fused. From all these properties, the structural formula of isoquine can be written as first, conformation by synthesis. The structure of isoquinoline can be confirmed by synthesis from cyanic aldehyde. It involves the condensation of cyanima aldehyde with hydroxylamine to form the corresponding oximine. The oximine on heating with P2O5 yield isoquinoline. All the ring atoms in isoquinoline are sp2 hybridized. The electron pair on nitrogen atom resists in an sp2 orbital and is not involved in the formation of delocalized pi molecular orbital. Isoquinoline consists delocalized 10 pi electron system and satisfies the Huckel rule. Isoquinoline can be written in the following resonating structures. The various pi electron density in case of isoquinoline can be shown below. Derivative of furan. First, furfural. It is obtained by the distillation of boron with dilute sulfuric acid. Manufacturing. It is prepared on the large scale from agriculture waste like oat hulls, corn, etc. by treating with dilute sulfuric acid, following by stream distillation. We know that pentosan are the polymer which are a kind of anhydrous derivative from pentose. These are hydrolyzed with sulfuric acid into pentose, which undergoes dehydrocyclization to furfural. Property. Physical. It is a colorless liquid with a characteristic odor. B. Chemically. It undergoes electrophilic substitution reaction to give 5 substituted derivative under suitable conditions. First, oxidation. Second, reduction. Third, decarboxylation. On heating with ZnCO4 MnCrO4 we get furan. Cannizzaro reaction. On heating with furfural, on heating with aqueous NaOH, phoric acid and the furfural alcohol result. Perkin reaction. When heated with acid anhydride and sodium acetate, we get furfurylic aryl acid. Benzyne condensation. On reaction with KCN, we get furoin. Classian condensation. Cassian condensation. On treated with acetone in the presence of base furfuryridine. Acetone result. Furfural give brilliant red color with aniline in acetic acid. Furoic acid. It is prepared by the oxidation of furfural with KMnO4 or with silver oxide. Furoic acid show all the reaction of a heterocyclic compound as well as carboxylic group. It can be reduced to furfuryl alcohol. When furfuric acid is heated with bromine, we get 2-bromofuran. Thank you. This chapter is complete.